Assalamualaikum warahmatullahi wabarakatuh. Lesson 45, Born-Haber Cycle. Soon you will realize that we are going to be very fast this semester. This is the last part of Chapter 1, Thermochemistry. We are going to learn about Born-Haber Cycle of ionic crystal, and we should be able to calculate unknown enthalpy using Born-Haber Cycle. Ionic bonding formation can be broken down into stages. Each stage involves enthalpy changes. Most we have learned in lesson 42. This cycle is often used to calculate lattice energy of ionic compounds. It is useful to predict the stability of existence of ionic compounds. The more negative the lattice energy, the more stable the compound is. A good example for discussion is the lattice energies for magnesium chloride MgCl and magnesium dichloride MgCl2. Notice that MgCl has lattice energy negative 753 kJ per mole, but MgCl2 has a more negative value, negative 2,526 kilojoules per mole. This shows that MgCl2 is more stable compared to MgCl because the value of lattice energy is larger or more negative. The same principles can be applied to enthalpy of formation. Another example is for NaCl versus NaCl2. NaCl2 almost does not exist under standard condition because the value of enthalpy of formation is positive. It should be negative. The more negative it is, the more stable it is. Right, this is your first Born-Haber cycle, example 1.8 of your course book. The Born-Haber cycle for sodium chloride solid. As you can see, and on the top of the cycle is the enthalpy of formation for NaCl. You can see this is the constituent element, sodium in the solid form and chlorine gas in gas form, forming sodium chloride, an ionic solid. And ionic solid, NaCl, comes from down here, Na plus gas and Cl minus gas. If you notice, this equation is the definition of lattice energy. Lattice energy, if I may repeat, is the heat change when 1 mole of ionic compound in its solid state is formed from its constituent gases ion. So this is also constituent element of NaCl, but instead of being in the standard condition, it is in gaseous ions. So this is actually a complete cycle. In Hess law, we learn about energy cycle method. Born-Haber cycle is a type of energy cycle method whereby we are going to apply Hess law in this cycle. So, as you can see, this is enthalpy of atomization, whereby sodium solid is transformed into sodium gas and the enthalpy of atomization is positive 107.8 kilojoules. And then Sodium in the form of gas will be turned into ion gas. And this is actually the ionization energy, i.e. it is positive 495.4 kilojoules. Now let's look at the chlorine gas. Before anything, we need to atomize the chlorine molecule. From molecule, we make it to become atom. So half of one molecule chlorine will produce one atom chlorine. So this chlorine atom would be in the form of gas. This enthalpy is called enthalpy of atomization of chlorine, positive 121.3 kilojoules. Right. After that, chlorine gas is going to be transformed into chlorine ion in the form of gas. So this is actually electron affinity because it gains electron. The value of electron affinity is negative 348.8 kilojoules. Now, this cycle must be completed with arrows. The first arrow is going to the right here, and then the arrow going down for the first column, arrow going down for the second column, and then sodium ion gas and chlorine ion gas will go up to form sodium chloride again. So, applying Hess law, we should be able to make up a formula. What is the formula? Delta H1 equals to delta H2 plus delta H3 plus delta H4 plus delta H5 plus delta H6. So, we are given all the values of delta H1, 2, 3, 4, 5. Will we be able to find delta H6? Yes. So let's recap the list of enthalpies that we have done in figure 1.8. Delta H1 is the enthalpy of formation of NaCl, sodium chloride. Delta H2 is enthalpy of atomization of sodium. Delta H3 is the first IE of sodium. Delta H4 is enthalpy of atomization of chlorine. Delta H5 is electron affinity of chlorine. And finally, delta H6 is the lattice energy of sodium chloride. All of these are listed in your course book. Note that delta H2 enthalpy of atomization is also can be called enthalpy of sublimation because the phase turns from solid to gas immediately. Okay, here is the calculation part. Delta H1 equals to delta H2 plus delta H3 plus delta H4 plus delta H5 plus delta H6. So we want to know delta H6. Insert all the values into the formula. Be careful of the negative sign and learn how to not make mistakes in the calculator. The final answer is negative 787 kilojoules per mole. This is another version of a Born-Haber cycle. If you read a reference book on thermochemistry, you can see there is another version of the Born-Haber cycle, and this Born-Haber cycle is using the whole equation in its energy level diagram. So this is basically energy level diagram. The y-axis is energy and the x-axis is the reactants or product or progress of reaction. So where is the enthalpy of formation? It would be here, delta H1, whereby potassium solid plus half of chlorine gas. So these are the constituent element in standard condition. It will form potassium chloride solid ionic compound. Right. So if the enthalpy is positive, delta H2, when it happens, it will go up. So here the difference is the K potassium solid becomes gas. So this is basically atomization of potassium. Now, going up is the enthalpy of atomization of chlorine, because we see here the molecule of chlorine becoming atom of chlorine in gas form. And going up, because the enthalpy is positive, it is going up. And here K atom becomes K ion in gas form. So this is basically the ionization energy. Now, here chlorine is turned into chlorine ion gas. So this is the electron affinity. It goes down because it's a negative enthalpy. And you can see here the lattice energy is the biggest. So this is how you are going to see the importance of lattice energy. The bigger or the larger the lattice energy, the more stable the compound is. So it will go from here straight down where it comes from. So this is a Born-Haber cycle rearranged and put in terms of energy cycle, energy level diagram. I just noticed that in your book, there is no line at the bottom of delta H1 and KCl solid. So could you please take your ruler and add this line, because it's quite important to be there, because it is actually where the spot is zero energy. Now let's do example 1.9. Name all the types of enthalpy changes shown in the figure 1.9. If you listen in detail my explanation previously, you would notice that delta H1 is the enthalpy of formation of potassium chloride. And then we go up, remember? So that one is enthalpy of atomization of potassium. Delta H3 is then enthalpy of atomization of chlorine. And then delta H4, you can see that the atom for potassium is turning into cation. And then electron affinity of chlorine, it turns into anion. And finally, the biggest and the largest enthalpy would be lattice energy of potassium chloride. Let's do question number 2 of example 1.9. In your course book, you can write the answer in small handwriting next to the delta H. So the question is, identify the types of enthalpy changes and calculate the lattice energy for sodium bromide. So delta H1 would be the first equation on top, and this is the constituent element in their standard state, standard condition. So it must be enthalpy of formation of sodium bromide. The ionic solid compound is this one. Notice that the bromine at room temperature is a liquid, so it is going to be vaporized first. Therefore, delta H4 is the enthalpy of vaporization, which is only 15.5 kilojoule per mole. Not much energy is used. And then for this molecule of bromine is going to become atom, and we use enthalpy of atomization delta H5. So delta H5 is enthalpy of atomization with the magnitude 112 kilojoule per mole. And then when it becomes atom, it will turn into an ion in gaseous form. So this is the electron affinity of bromine, delta H6. Now this is the second column. Let's move to the first column. Sodium in solid form will become sodium atom. So delta H2 is enthalpy of atomization or sublimation of sodium. And then sodium gas will be turned into cation in the form of gas. It is delta H3, which is the ionization energy. Delta H7 is the lattice energy, which we want to calculate. So let's look at the calculation. We are going to use all this data. There you go. This is the list that I have told you before. And this is the formula. Delta H1 is the enthalpy of formation. Apply Hess law. Delta H1 equals to delta H2 plus 3 plus 4 plus 5 plus 6. Insert all the values. And please remember to do the calculation well, because this is a negative value and this is also a negative value. So we are going to get a negative value here, which is negative 767.5 kilojoules per mole. Question number 3 is even more challenging because you have to construct the Born-Haber cycle for yourself. And for which ionic compound? Calcium bromide. And you have to find the enthalpy of atomization of calcium. And you have to compare the lattice energy between CaBr2 with that of MgCl2. And then we need to explain our answers. The data is given below, and we have IE, first IE, second IE, enthalpy of vaporization, and atomization of Br, EA, lattice energy, enthalpy of formation. So what is not here is the enthalpy of atomization for calcium. So let's do the Born-Haber cycle in the next page. Okay, so the first thing that we need to do is we write the equation for the formation of calcium bromide. So Ca, the standard condition, is solid, and then Br2, the standard condition, is liquid. So we react them together and it will form CaBr2 solid. This is the enthalpy of formation, which gives us the value of negative 666. Okay, and then we are going to form calcium atom in the form of gas. So this is enthalpy of formation of calcium, enthalpy of atomization of calcium, or this is the one that we need to find, delta HA for calcium. All right, and then we are going to use IE1 to form Ca plus gas, and then IE2 to form Ca2 plus gas. So this one would be 590, and then this one is 137 kilojoules per mole. And then Br2 here is going to use the enthalpy of vaporization, which is 31 kilojoule per mole. It becomes Br2 gas. And then for this one, we want to make Br atom, but can you see that here in the molecule there is 2 atoms? But here we must do it 1 atom. So is this balanced, this part? No, it's not balanced, right? So for 1 molecule of bromine, we are going to produce 2 atoms of Br. So what happens here is, this is, the value is 112. 112. Let's look at the definition of enthalpy of atomization. Which part is 1 mole? The enthalpy of atomization is the heat change when 1 mole of gaseous atoms is formed from its element under standard condition. So the 1 atom must be at the product. 1 mole of gaseous atom is produced. So this is like we are having 2 reactions. Now, 1 reaction is 112. If you have 2 reactions, 112 multiplied by 2. So we have to multiply the enthalpy of atomization given in the question by 2. Because we want to make this equation balanced. This cycle also must be balanced. So this one will go down to Br in the form of negative anion, in the form of gas, and this one is given in the question negative 325. This is also multiplied by 2 because there are 2 reactions simultaneously happen. Now let's complete the cycle. Okay, plus and then go up. This is the lattice energy. So the lattice energy given to us is negative 2176. Now we are given this one, this, and this. Are we able to find this? Yes, using Hess law. So if you have drawn this Born-Haber cycle, you should get as much as 4 marks. When you answer what is delta H, you are going to get another 2 marks. Alright, let's look at the answer. What is delta HA for calcium? So given to you here, the answer for delta HA or delta H2 is 178 kilojoule per mole. Now, the next part is for us to answer the question about lattice energy. It wants us to compare the lattice energy of CaBr2 with that of MgCl2. Now, both Mg2 plus and Ca2 plus have the same value of charge. So, we compare the size. It turns out that Mg2 plus has smaller ionic size. So, this one, you have to go back to chapter 4, Sem 1, or you can go straight away look at the periodic table at group 2. After that, we compare between Cl2 and Br minus. Which one is smaller? Cl minus. So basically, Mg is smaller, Cl is smaller, and we can say that the nuclear attraction, the ZEF, you remember ZEF? The ZEF is stronger in MgCl2 because it's smaller. This makes MgCl2 has more negative lattice energy compared to CaBr2. So we have to remember from the lesson 42 regarding enthalpies. When we learn about lattice energy depends on the size and the charge. So the smaller the size, the higher the lattice energy, and the higher the charge, the larger the lattice energy. Alright. Your task is to do practice 1.4 question number 1. Here you have to construct a Born-Haber cycle from scratch, CaCl2, but the values are not given. So you just label enthalpy of formation, enthalpy of atomization, and so on. For question number 2, you have to draw the Born-Haber cycle, and then you have to label the enthalpy of atomization of barium, chlorine, formation of barium chloride, IE, second IE, and lattice formation. What is not there? Yes, electron affinity. So you have to find the value of electron affinity, and then you have to comment on why lattice energy of barium chloride is different from magnesium chloride. So you should get the answer for electron affinity of chlorine is negative 347 kilojoule per mole. For question number 3, you have to form Born-Haber cycle for magnesium chloride, MgCl, not MgCl2 but MgCl. So the answer would be negative 130 kilojoule per mole. For question number 4, you have to draw the Born-Haber cycle and you have to find what enthalpies are not there listed in the data. So I believe I cannot see there the enthalpy of formation. So once you find the enthalpy of formation, you would know that it will give you a certain value, that value will tell you why NaCl2 cannot form under standard conditions. So I've shown you the Born-Haber cycle, how to draw them and how to calculate the unknown enthalpy. You also must know how to explain the lattice energy for certain compounds. Thank you very much for listening, and I'll see you again soon. Assalamualaikum.